This is the last lesson, and what you're going to do today is a little bit of cryptography, in particular cracking password hashes. And I thought, especially since you're in business school, it would be worth talking about why this kind of cryptography is used. And especially since, as I discovered the hard way, this stuff is very frequently misunderstood. This is a talk I gave at NASA a few years ago. And what happens here, there was a headline in 2012. In January, the headline said that we had the worst computer security incident at any college ever at City College. And this went around the world. It went all over the place. It was covered by international press, and it was completely false. And I was surprised. I woke up in the morning. When it came out, went to work the next day, and people started calling me, what happened? What's wrong with the security at the college? And I said, I don't know anything. And so they called the help desk, and the help desk said, we don't know anything. The chief technology officer had gone to the press and not told anybody at the college anything. So nobody had any idea what he's talking about or what it means. And that right there is a serious failure. If you have some kind of security problem, the first thing you have to do is internally get your ducks in a row and tell your public relations people and your help desk people what to tell people, because you know what they're going to say. When they see that, they're all going to freak out. Should I use my computer? Do I need to change my password? Do I need a new credit card? What does this mean to me? You can guess what the first few questions are going to be, and you have to have clear answers to those questions right at the fingertips of the people that are going to be called. And we had nothing, which was the first clue that something very wrong was happening here. And this is the story. There was a campus newspaper and a campus journalist that was impressed by the chief technology officer and just printed everything he said as if it was fact without verifying any of it. And so this is the story that the chief technology officer gave people. He said that the machines on campus had all been infected by viruses for 10 years, and that this was obvious, and all the teachers and stuff told students not to worry about it, and everything they'd been typing into those machines had been being stolen by Russian criminals. Thank you. And teachers like me were there and telling people there's nothing wrong. And this, I thought, was pretty interesting, because I had in fact been seeing the state of campus machines for 15 years, and my students had done security audits at the college twice in my CISSP class, and I knew very well what the security problems were, and nothing like this was happening. And so they called this company, a San Francisco company called USDN, run by a guy who's kind of a lunatic, and he came in as a contractor, and what he did was he put on some special network forensic device of his own invention that we were not allowed to audit. This is another red flag. He said, I have a secret database with information from the U.S. Department of Defense and FBI with secret data that you can't see that lets me know who all the criminals in the world are that are taking over computers, and I can tell if the traffic is going to those control centers, and that proves they're infected. But I'm not using any commercial tool that you can look at ratings of, and you can't examine my software to see what it does. You just have to trust me that it's working. And all of our traffic was redirected from campus to some off-campus site where his tool investigated it, and that was the basis for all this. And supposedly, so here it is going around the world, IEEE published this article that we were infected and that we've been infected since 1999 and done nothing about it because his tool was finding really old viruses. And in particular, this was pretty hard for me to believe because the physical equipment had been replaced twice in that time period. And it's kind of hard to see how a virus survives complete replacement of the computer. And here it went to TV news, and this is the San Francisco Chronicle, I think, just all over the world. And so he brought down newspaper reporters and got them to take pictures of the labs to get his name in the paper, and didn't tell anybody inside the college anything. So in the world of computer security, we often talk about outsider threats. You have firewalls and stuff to stop attacks from outside, and you have insider threats, like people inside your company that are bribed or malicious or just incompetent that leak data. But here we had a new one, the diluted insider threat. What do you do when a high-privileged person inside your company is completely insane? And I think the entire nation is now living through another example of this. I knew that none of this was true. We ran antivirus in all the PCs, we run deep freeze, we have a layer 7 firewall protecting the network, we replaced the hardware. There is very little malware on our machines, and I knew that because there was a time when he had a malware problem back in about 1998. And you couldn't get anything done, and I'd clean off the malware in the lab and it'd be all infected again the next week. And because of that, they instituted these measures, and it worked. There was very little malware in those machines. Like I said, there was a security audit, And I did another security audit with my students, and there was nothing this bad found, just a few little things. So there was supposedly a report from that contractor proving this, but he said none of us were allowed to see it because it was confidential. And the vice chancellor, eventually a lynch mob occurred to try to get rid of this guy, led by the vice chancellor, and I was at the front of it. And I said, how can we not be qualified to see the report that we paid for? I can see how maybe you don't want other people to see it, but how come we're not qualified? And he said, because the FBI is investigating. Only the FBI can see that report. But he didn't know that my FBI contacts were better than his, and the FBI had already called me to see if we need help. So I knew that he was just completely lying about the FBI investigation. And after it became clear that he was going to be fired, he took that confidential report and published it in the newspaper. So that was how confidential it was, and here it is, the confidential report. He had a list of how it's everybody else's fault that we have all these viruses, everybody is just covering it up. And here's the 1,400 command and control botnet events showing that our machines are under remote control. And on April 3rd, we finally got the list of infected machines, 4,500 infected machines out of 10,000 total, which is indeed terrible. And now I could go look at those machines, and I looked at the 25 that contained Zeus, and they had no infections. So it was completely fake. And one thing that's kind of funny here is he claimed to find 200 Windows viruses on our Unix DNS servers, which is impossible. And it showed that his traffic inspection was just done incorrectly, and he was taking innocent traffic and interpreting it as the virus traffic. So we finally managed to fire him, which almost takes an act of Congress in civil service. Then he wrote a letter to all the trustees in a newspaper blaming everybody by name, the vice chancellor, the network administrator, me, and other people, and bringing back one of the several times the college has been hacked by criminals to punish me for teaching these classes. On it went. There was someone that claimed he had stolen a couple of dozen teachers' accounts and was spending money out of their PayPal, which turned out to be false at the time. But anyway, this is another one of the guys that contacted the college to try to get them to throw me out. It's the cost of doing business in this field. And anyway, he was suspended and banned from campus. So that was a fake breach. And this thing was fake in two important ways. In the first place, it never happened. But in the second place, even if this had happened, it is not a data breach. Because if students go up to use machines in the lab, and the labs happen to have viruses on them, and then they do something like online shopping and get their credit card stolen, that is not our problem. Those machines you use at your own risk. A breach is when the data we collected from people is lost. If we gather data from students for enrollment and mailing and grades and health care, and then someone steals that data, now we're in trouble, because that was our property and we had an obligation to protect it. So here's how real breaches happen. I've got a demonstration here. Let me bring up my Windows machine. All right. And let's get rid of this unnecessary junk and run Havij. All right. So I'm going to keep closing junk until we get down to it. All right. So ad.samsclass.info /sqlol-raw. There we are. Okay, so here is a simple website storing data the way websites really do store data. All right, this has just a simple database with just a few records in it, and it has a search field here, so you can type in a name. So if I type in a name like Fred, it searches, and there is nobody named Fred. If I put in a wildcard, like % is the wildcard in this SQL language, then you see the data, and so there are 5 names in here. Silly names that somebody else put in this demonstration tool. So the point with SQL injection is if you put in a name like O'Neill with an apostrophe in it, you then get a strange error message. And this error message says you have an error in your syntax, which you were seeing a lot when you were writing Python. This is very, very bad, because what it means is the language that actually fetches data out of databases for websites like this is shown here. And here is the query. Select username from users where username like O'Neill. Let's focus in on the start of this and show you how this works. Okay, this is the command. This is an active command, select. Then username is the field to select. This is the name of the table. And here's the condition, username like O'Neill. But because I put in that apostrophe, the parser is matching it with this apostrophe and looking for a name like O, and then Neil it expects to be a command. So this is a command injection vulnerability. This is called SQL injection. It is the most important security flaw in the world. More than 95% of all stolen data has been stolen by this technique. And what happens is, because the administrator did not think of this when they designed their database, the software that runs it, I can put commands in the names and they will execute. And the reason it's complaining is because Neil is not an active command. It's not a valid command. So all you have to do is send up more carefully chosen queries, and you can just pump the data out of the database. And you don't even need to know what you're doing, because there are free hacking tools that will do it. So if you go here and make a simple example with query equals X that's searching for it, if I just copy that URL and put it in this tool called Havij, which is Arabic for carrot, it's an Arabic hacking tool, then analyze the database. And down here at the bottom, it's going to send some traffic and presumably call up the answer. Let me see, I don't have HTTPS, that's good. That should work. It's irritating me by being too slow. There we go. Connection aborted due to a timeout. All right, let's just stop it and just try it again. It may just be slow networks. ADC, yeah, that's the right query. It's going to annoy me if it doesn't work, because this is a fun demo. Let me just check my networking. Yeah, that's not the problem. How rude. I'm just going to close it and start it again. Give it one more try, and then I'll skip it and just talk about the results. But it's more fun to see it happen live. So you put in the target query there, and then analyze, and analyzing, retrying to find keyword. Yeah, that's the right query, all right. All right, well, if this is not going to work, I'll just talk about it then. So anyway, the point is, when you see that SQL syntax error, that means you can hack it. So here's World Investment News. This is a real website. I didn't know at this time it was illegal to do this test, so I tested hundreds of websites and I informed the administrators and such. Then when someone finally got mad at me, my lawyer told me that it violates American law to do that, which is very annoying. Almost everything funding security is illegal. But anyway, I cheerfully did it. I even gave students homework where they would warn these people about their vulnerabilities. Here's CIA services, an error in their SQL syntax. There's a lot of websites on the internet with this vulnerability. Approximately 11% of all websites have this flaw, and that means all the data they store is just wide open for hackers to steal it. Here's many examples, and this is what happens if this tool was only going to work. You can just click a couple of buttons and out comes all the data, names and social security numbers. You don't even have to know what you're doing. It automatically sends the queries up to the server. And the exact commands are down here. You have another tool from SQL Map, but it doesn't really matter. So what happened in 2011, there was an explosion of activist hacking in America, where a bunch of people hacked to make a political statement and then would just dump the web data publicly, which is not normal. Usually they keep it private to make money. And so it was possible to test the security of passwords on the internet. And this Team Ghost Shell dumped about 20 or 30 companies worth of data, which I then analyzed. So they had some kind of nonsense political reason why somehow they're saving the world by doing this, which they justify. And then they had a long list of all the people they hacked. And so I said, how do people store passwords anyway? And I thought the worst thing you could do is store passwords in plain text, but that's not true. You can be even stupider. Here's a company called Buchanan Bond Exchange, some kind of investment company. And here's the password, Buchanan Bond 1, Buchanan Bond 1, Bond 1. Most of the passwords are the same and are equal to the name of the company plus 1. So they're trivial to guess. Here's Reeves and Associate. This is a law company. Most of their passwords are just 1234 or JJ Law 321. Most of them are just some default value. So you can get in these accounts and mess with these people. Here's a company called Sparklan. It sells auto parts, and almost all the passwords are Sparklan, just the name of the company. So I used to work at a company, and there was a burglar alarm, and the boss set the code to 1234. And the point is, somebody made him put in the alarm. He didn't want to, so he just put in an obvious code he wouldn't forget, because he didn't really have any respect for the security. And it's obvious that these people have the same attitude about passwords. Some idiot made me put in a password. I'm just going to put in the first thing that comes to mind, so I can tell them we have a password. Here's B-forward transactions, and this one, let me blow it up a little. This one has real data. This is names of their customers with addresses and dollar amounts, which is really bad because that's PII. If you lose people's names, that is not a breach of personally identifiable information because many people have the same name. The law says if you lose their name and another thing that identifies them, like their birthday or their driver's license number, then you have had a personally identifiable information breach and you must take a bunch of painful action, like notify people, pay fines, buy them credit insurance and such. And here's another, this is a more common situation. This company had just passwords, and at least they're all different, but they stored all the passwords unencrypted on their server. And Facebook did this too, and they got hacked and lost all their passwords. The entire database was stored in plain text on the internet, and it was protected by an administrative password of happiness, no numbers or anything, and they were sued with a class action lawsuit that low security actually violated their promise to maintain reasonable security. So here's people that have made some attempt to protect their password. B-Forward Japan sells auto parts in Japan, and their terms of service say we employ commercially reasonable security methods to prevent unauthorized access. And that consisted of running a web server with a SQL injection vulnerability so everybody could steal the data. But if they steal it, the passwords look like this, MZRJD2 ending in equals. That's called base 64 encoding. It's not encryption, it's just taking the bytes and using 6 bits at a time instead of 8 bits at a time. So you can just trivially reverse it with online sources, and here's one. That long mess ending in equals turns into this, HV-3NCL, which is a pretty good password, but they stored it in a way that it might as well have been plain text because there's a trivial mathematical operation to recover the real password. So here's what a lot of people think is secure. You take MD5 hashes or SHA-1. These hash functions combine all the bits in a file and make a fingerprint that's always the same length. The main purpose of them is to see if files have been altered during a download. So you download a file, you calculate the hash. If the hash matches, that means you got the whole file and it wasn't damaged in transit. But people use them for password hashes because they do not understand that this is not wise. So here is what an MD5 hash looks like. This might be a SHA-1, looks a little long. And this whole mess, the hackers who weren't very good at cracking password hashes, they could still crack this one. That's Hiawatha. And you'll be cracking these later. The hash function is not reversible, like base 64. The only way to crack it is to have a list of candidates and hash them all to see if you find a match. So you have to just get a list of possible passwords, which is very easy these days because so many data breaches have happened that there are something like 4 billion known stolen real passwords that you can get in a list. So you can try, and that includes pretty much every password that a human can remember. So you can crack MD5 passwords here. I went to an online tool that just looks it up in a database, and here it found board7R5A, which is a pretty obscure password, but the hash was in the database, which means that was used somewhere else and somebody cracked it before. MIT has a form where you can report these breaches, and I told them I don't know if they did anything. MySQL has this other kind of hash. There's just a long, shorter list of characters there, but it's just a different algorithm that can also be reversed. And you can crack it with a variety of tools. This is a SHA-1 hash. So once you do breach a database and steal the data, you often have this kind of encrypted stuff. And the question is, can you really recover the plain text passwords? And if passwords really were like 10 random characters, with not a word plus a number, but just random characters, you probably could never crack them. But nobody uses passwords like that unless they use password managers, which is a very good idea, because they can't remember them. So I'll just mention the password hashing algorithms. There is a correct algorithm to use, which is what Linux computers and the Mac use, which is bcrypt, where you do hashing thousands of times just to make it slow. You add a long random string to each password, and then you hash it with SHA-512, which is the longest hash, and then you do it 5,000 times. And the point of that is if an attacker tries to have a large dictionary and calculate all the hashes, it takes them a very long time. You make it so that it takes about 1/10 of a second to calculate one hash. And when you log in, you type in the password, the computer calculates the hash of your password and compares it to the stored hash, and if you have the right password, it matches. But it doesn't store your password anywhere. And it really slows down attackers. And the end result is Windows passwords, you can try 100 million guesses per second because they use a terrible algorithm. And Linux passwords, you can try 100 guesses per second. So it's 1,000,000 times stronger. And anyway, so I just want to point you to the project where you start doing this stuff. So go to this page where you go to samsclass.info and click on Hult. You've been here before. And down here is where cryptography starts with password hashes. And I'll just demonstrate a bit of it here like before and then go around and see how people are doing. So here's the point. Password in the Microsoft Windows machine will turn into this thing, 88467. And by the way, if you want to crack Windows password hashes, you can just Google them because there is no randomness. If 1,000,000 people have the same password, they all have exactly the same password hash, which is one of the many defects of this. So let's try some of this in Python. Let me go here and, all right, and nano hash1.py and put in that stuff. So what this does, remember the whole reason Python is easy is somebody else has done all the work for you. So it imports a hash library, then I take from the user a password, and then I print the MD4 hash. MD5 is the one you saw there. Windows uses MD4 because their hash algorithm was designed in 1993 before MD5 had been written, and for some reason they have never updated it in the nearly 30 years since. So if I run this Python, hash1, and then I put in a password like password, I get a weird, useless answer. I don't get the answer I expected. I get hash object at some address. And this is a clue that Python is a little more complicated than you might imagine. What you have created is a hash object, which is a data structure containing more information than just the hash value. And if you want to see the actual hash value, you have to add it hex digest to get the hexadecimal plain number out of it. So I'll modify that file, and at the end here you put .hexdigest, and that will actually print out the password in a way you can see it. If I put in PASSWORD, now it prints out this number, which is a hash. But I don't know if you remember, this is the wrong hash. It should be 88FD something. So this is not yet the Microsoft password hashing algorithm. There's one more step. Microsoft uses Unicode, not ASCII, because it's an international operating system and you can use Japanese and Arabic characters and everything. So what you have to do is you have to encode this thing with the international Unicode and then do the hex digest. And you do that by adding password encode UTF-16LE. So let me put that in. And so it's here, password.encode, which encodes it with 16 bits per character instead of 8, which is what you need for international languages. And even though it only uses 8 of the bits for English, it does change the pattern of bits, and that means that you get a different hash. So if I do that, and then put in password, I get the right answer, 8846. Now I'm able to create Microsoft password hashes. And now you can start cracking hashes. You can make a hash dictionary for all the 2-digit passwords for 2-digit pins going from 00 to 99, and then you could look those up. And then I have some hashes here to crack. I've given you a pattern of them. These are all CCSF-username-pin. The pin is a 2-digit number, and the username is the lowercase name. And here's 3 password hashes. This is the way Windows 7 password hashes really look. The first part here is an old obsolete system called the LM hash, which was so insecure even Microsoft couldn't stand it anymore, and they got rid of it. So that's why these are all the same. That's just a useless placeholder. The part after the colon is the modern Microsoft hash, the so-called NT hash, the new technology. That is the part that you will be able to create with your program. So you can try all the options and crack these passwords, and then there are some challenges where you crack increasingly secure hashes to see that even many rounds and even an unknown number of rounds does very little to hide your data. So I'll go around and see how people do on that stuff. Just carry on with this one. Let me